Hello ladies and gentlemen, this is Ms. Skokin. We're in Chapter 8, Right Triangles and Trigonometry. We're going to continue the work that we've been doing with similar triangles, and we're going to expand into only similarity in right triangles. Let's take a look at our objectives for Section 8-1. Use geometric means to find segment lengths in right triangles and apply similarity relationships in right triangles to solve problems. The new vocabulary includes geometric mean and altitude. So we've got 5 little warm-up questions. I'm going to ask you to pause the video while you work on those and turn the video back on when you're ready to check your work. Remember that when you're simplifying those radicals, you want to end up in simplest radical form. See you back in a minute. Just a few brief comments on these problems. Remember, in number 1, order matters, so you need to be able to recognize in 2 similar triangles which are the angles that correspond to which, so that you can put them in the proper order in the similarity statement. In numbers 2 and 3, remember that simplest radical form means you do need to do some factorization so that you can pull the squares out of the radical and everything that's not a perfect square stays inside. In number 4, remember that in general we want to give our answers in, if we have a nice round decimal, we can do that, but otherwise we want to end up either in a mixed number or in an improper fraction. And in number 5, remember, order of operations is backwards when we're solving. So the very first thing that we're going to do is divide by 2 on both sides before we take the square root of anything. Now let's take a look at Theorem 8-1-1. It says the altitude to the hypotenuse of a right triangle. So before we continue on, let's go ahead and identify the altitude. The altitude is the segment that goes from the right angle to the hypotenuse, but meets the hypotenuse at a right angle. This is the altitude of a right triangle. So let's go back. The altitude to the hypotenuse of a right triangle forms 2 triangles. And let's take a look. We have triangle ABC. We also have 2 smaller triangles that were now formed by drawing that altitude. The 2 smaller triangles are triangles ACD and CBD. So I've drawn them in purple and orange so we can distinguish them from the larger triangle ABC that we started out with. Anyhow, the altitude to the hypotenuse of a right triangle forms 2 triangles that are similar to each other and are similar to the original triangle. So that means that all 3 of these triangles are similar to one another, meaning the angles are all congruent, corresponding angles are congruent, and the side lengths are all proportional. So we have a lot of power when we understand that, because we can use that to solve different problems. Again, a commentary, the altitude is the perpendicular segment between the right angle and the hypotenuse. And the next thing that we want to do is reorient, we want to redraw all 3 triangles and reorient them so that they have the same orientation and we can compare them to one another. So here are the 3 triangles. We've got angles ABC, ACD, and CBD. We need to mark those right angles in each of them, and then we can see, now that we've split them apart, yes, they are all similar. When we see the same orientation, it's much easier to see. When they're all put together, it's a little bit harder. But just remember that when you're doing one of these problems, you are more than welcome to break them apart if you need to. The other thing that you can do is you can color code them, as I did in our Theorem 8-1-1 box. All right. Once we've got that done, we can start applying this new understanding to example number 1. In example number 1, it says, write a similarity statement comparing the 3 triangles. It is definitely helpful and useful to be able to see the 3 triangles separately. The easy one to see is the large one, but when we come across these 2 examples, it's nice when we can distinguish between the medium size and the smallest triangle. Remembering the order matters, I'm going to put my triangle names in the order, the smallest angle first, then the next angle, and then the right angle last of all. So I'm going to say triangle UVW is similar to triangle UW WZ, Z being my right angle for the medium-sized triangle, and that's similar to triangle WVZ on the smallest triangle. So again, same order holds through each time. And there's absolutely nothing wrong with writing it out so that you know exactly what you're doing and you make sure to get it right. Okay, you've got a now you try, and it's your turn to write the similarity statement for the 3 triangles. Turn the video back on when you're ready to check your work. The question often comes up, do you need to give the angles in a specific order? For example, the small, medium, and large. And no, you don't have to do that. You just have to be consistent from triangle to triangle. So if you're writing a similarity statement, all 3 triangle angles need to be in the same order as each other. And you can see for the now you try, the way that I've done it is the medium-sized angle first, the right angle, which is the largest, second, and then the smallest angle third. Doesn't really matter what order you start in, but the other 2 triangles need to be in the same order. Okay. Imagine we have a list of numbers such as 2, 6, 18. How do we get from one number to the next? And you probably immediately recognized that we just need to multiply each number by 3 to get to the next number in the list, and that's correct. You may remember that this is called a geometric sequence, and you learned about this in Algebra 1. You also learned that the number that you multiply by, in this case positive 3, is going to be called our common ratio. Now imagine that we have the same list, but we don't know the middle number. So we have a number that we're going to call A, which is 2. We have another number that we don't know, which we're going to call X, and then we have another number we're going to call B, which is 18. And one of the things that we can say is we can set up the relationship that 2 is to X as X is to 18. 2 is to X as X is to 18. That brings us to this format that we've got listed here. A is to X as X is to B. And we remember solving proportions. We can use the relationship that we see right here to come up with x squared is equal to 36. And we know that that's going to mean that x is equal to plus or minus 6. So 6, either positive 6 or negative 6, is the geometric mean between the numbers 2 and 18. Now we already knew what the answer was because we saw the list beforehand, but this is describing how we come up with this idea of the geometric mean. We have 2 numbers. If we want to find the geometric mean between them, we multiply them and then take the square root. So example number 2 has us finding geometric means, and we're going to follow that same pattern. This time we're going to find the geometric mean of the numbers 4 and 25. That means we have a list 4, x, and 25. We can set this up as 4 is to x as x is to 25. Now I know that very often we're able to do a lot of math in our head, but I'm not worried about this specific question. I'm worried about you being able to do questions that have a lot of complex expressions, not just the numbers 4 and 25. So remember, you're learning skills and setting up good working habits that are going to take you far beyond geometry honors. Okay, we end up with x squared is equal to 4 times 25, which we know has the product of 100. We take the square root of both sides and we end up with, of course, x is equal to plus or minus 10. All right. When we find the geometric mean between 5 and 30, we're going to start out the same way, knowing that we have a number 5, another number x, and another number 30. We're going to set up the proportion. 5 is to x as x is to 30. And then we're going to use our cross multiplication, resulting in x squared is equal to 150. Now we know 150 is not a perfect square, so we're going to use our factorization. We know that we can get 150 by multiplying 25 and 6, 25 is a perfect square, and then 6 is going to stay underneath the radical. We can't pull him out. So when we take the square root of both sides, we're going to end up with plus or minus 5 root 6 as our final answer. There's a now you try on the next page, and I'd like you to go to the next page, turn off the video, practice doing those two geometric means, and then turn the video back on when you're ready to continue the lesson. See you back in a minute. Turn the video back on when you're finished with the now you try. Chances are the biggest challenge you're going to have with these geometric mean questions when they're solved algebraically like these is showing your work properly. So remember, if you're doing any work in your head or in your calculator, document it on paper so that if something goes wrong, you can be given partial credit. And also remembering no work equals no credit. We're establishing good habits in geometry honors for the rest of our high school and college careers in math. All right, let's see how are geometric means used in geometry. We can use Theorem 8-1-1 to write proportions comparing the side lengths of the triangles that are formed by drawing the altitude to the hypotenuse of a right triangle. So you can see that we're starting out here with the large triangle, triangle ABC. We've drawn the altitude, segment CD, from the right angle to the hypotenuse, splitting the hypotenuse into two lengths, X and Y. Just a quick reminder about the way that we name triangles. And you will notice that where we have angle A, if we go directly opposite that, we have side lowercase a. Where we have angle or vertex uppercase B, if we go to the very opposite side of the triangle, we have side length lowercase b or side lowercase b, and the length can be listed as lowercase b or AC with no bar over it. Then we have vertex C, which is our right angle, which is directly across from the hypotenuse, which has length lowercase c for side lowercase c. So it's just a reminder that this is the way that we name triangles, and we're going to be using this pretty much throughout. You're going to be using this throughout pre-calculus and beyond. So I wanted you to know that naming convention. We're going to be talking a lot about ratios of side lengths, and so on our first venture into the ratios, I want to look at the ratio between the long leg and the short leg. Now just a reminder, when we've got a right triangle, we have a hypotenuse, which is directly across from the right angle. We have legs for the other two. Now in this case, because it's not an isosceles, we have a short leg and a long leg. If we had an isosceles right triangle, they would be of equal length. So when we look at the ratios between the long leg and the short leg, on the big triangle, triangle ABC, the long leg is side B, the short leg is side A. On the medium-sized triangle, the long leg is side Y and the short leg is side H. And on the little triangle, the long leg is side H and the short leg is side X. Now, why is this important? Because we can see the beginnings of what's going to be a proportion that's going to help us solve problems, because we see H appear in two of the ratios. That's going to allow us to say that H is the geometric mean of the numbers X and Y. In geometry, that means that H, the length of the altitude, is the geometric mean between these two lengths, X and Y, that were created when we drew the altitude of the right triangle. Remember that another way to write this is that H squared is equal to X times Y, or we could say that H is equal to the square root of X times Y. That is the relationship that relates the altitude to the two pieces of the hypotenuse. Let's take a look at another relationship now. This time, let's take a look at the ratio between the hypotenuse and the short leg. And we're going to start off with the big triangle again. So on the big triangle, the hypotenuse is side C and the short leg is side A. I'm going to skip now to the small triangle. And on the small triangle, the hypotenuse is A and the short leg is X. And then on the medium-sized triangle, the hypotenuse is B and the short leg is H. Okay, once again, we see that A appears in two of these ratios. So what that means is, once again, we can rewrite this as using the geometric mean. A is the geometric mean of side lengths C and X. Another way to write this is A is equal to the square root of C, the whole hypotenuse, times X, the piece of the hypotenuse. You may have guessed by this time that we're actually developing the relationships that we're going to see in the corollaries about geometric means 8-1-2 and 8-1-3. That means that we have one more to go because there's one more relationship to write about, and that is going to be when we take a look at the ratio between the hypotenuse and the long side. Okay, once again, I'm going to start with the large triangle. The hypotenuse is C, the long leg is side length B. Then we're going to go to the medium-sized triangle where the hypotenuse is B and the long leg is side length Y. On the little triangle, hypotenuse is A and the long leg is side H. But what we notice is B appears in two of the ratios, so we can say that B is the geometric mean of the numbers C and Y, or we can write B squared is equal to C times Y. And if we took that a step further, we know we would write B is equal to the square root of C times Y. You've seen where all of these relationships come from, and it's all summarized here in the corollary box. I'll let you read those for yourself. Now, just a reminder that you are given all of the theorems, postulates, and corollaries in your sheets when you take a test. However, you need to know how to use them, and you need to know what those mean, and you're not given diagrams, okay? So you'll be given the words like the length of the altitude of the hypotenuse of a right triangle is the geometric mean of the lengths of the two segments of the hypotenuse, and you need to know what that's referring to. So let's take a look. On the next page, we're going to have example number 3, where we're going to be able to apply these new relationships to some problems. In example 3, we want to find the lengths x, y, and z on the triangle, but let's start by labeling it. We've got the hypotenuse, the altitude, and the two legs labeled. And now let's remember the relationship between the altitude and the two pieces of the hypotenuse. If you remember, the altitude is the geometric mean between the two pieces of the hypotenuse split by the altitude. In our example, the altitude is length 6, so 6 squared is equal to, and the two pieces of the hypotenuse measure 9 and x, and we're multiplying those numbers to each other. So 6 squared is equal to 9x. As we solve for x, we know that it's going to be equal to 36 divided by 9, or 4. So x is equal to 4. We also remember that there's a relationship between the leg length and the piece of the hypotenuse closest to it and the entire length of the hypotenuse. So let's set that one up. Y squared is equal to x times x plus 9. Now, just as a reminder, x is equal to 4 we found in the first part of this problem. So we can actually plug that in. And that means that y squared is equal to 4 times 4 plus 9, or 13. Of course, we square root both sides, and we end up with y is equal to the square root of 4 times 13. And 4 is a perfect square, 13 stays inside the radical, so we end up with y is equal to 2 radical 13. Just a reminder, this time we're not doing the plus or minus, because we're talking about lengths, and lengths cannot be negative. Let's set up what we need to find the length z. So this time we're going to say the leg length is equal to, or I should say, is the geometric mean of the piece of the hypotenuse closest to it times the length of the whole hypotenuse. So that's going to look like z squared is equal to 9 times 9 plus 4, which is still 13, And when we take the square root of both sides, we're going to have z is equal to the square root of 9 times 13. 9 is a perfect square, 13 is not, so we're going to have z is equal to 3 root 13. Now remember, we found all three lengths, x, y, and z, and we used the corollaries to the geometric means in order to help us out with those. But you don't have to do it that way. You can also find one or two of the values using the corollaries of the geometric means, and then you can use the Pythagorean theorem. That is another right angle tool that you can always use. I'm going to recommend, though, that you try to use these relationships to solve the now you try instead of the Pythagorean theorem, but if you really get stuck, go on and use the Pythagorean theorem. So you do have a now you try to work on. Use the example that we just completed together as a model and turn the video back on when you're ready to check your work. See you back in a minute. If you have any questions about finding x, y, or z on this example, definitely bring them to class. We have more practice on the next page with example 4 that gives us a real-world application of using the geometric means with similar right triangles. Anytime we're working on a word problem, we need to make sure to read the diagram and read the information in the problem carefully so we get all of the important pieces of information that are going to help us solve the problem. And so let's go ahead and get started reading. To estimate the height of a Douglas fir. Okay, so right there we know that we're looking for the height of this tree. It goes on to say, Joe positions himself so that his line of sight to the top and bottom of the tree form a 90-degree angle. So that means we have a 90-degree angle right here at Joe. His eyes are about 1.6 meters above the ground, and he is standing 7.8 meters from the tree. What is the height of the tree to the nearest meter? So they're telling us to round to the nearest meter once we get done. Now let's just take a look. We started out with a big triangle, and we drew the altitude, which is Joe's line of sight from his eyes to the tree. And that's what I have highlighted in purple, and that created two smaller, similar right triangles. So what we're actually looking for is the length of the hypotenuse of the big triangle. And we know that there's a relationship between the pieces of the hypotenuse that were split by drawing the altitude. So let's set up the relationship using the altitude. Remember that the altitude is the geometric mean between the two pieces of the hypotenuse. So I've set it up in words. Altitude squared is equal to hypotenuse piece 1 times hypotenuse piece 2. We're going to plug in the numbers that we've got now. Altitude is 7.8 meters. That's equal to 1.6 meters. And that's going to be times x, because this is the length that we don't know. So x is going to be equal to 7.8 meters squared divided by 1.6 meters. This is going to end up giving us a result of that higher piece of the hypotenuse being about 38 meters. But remember, what we're interested in is the whole height of the tree. And the height of the tree is 1.6 plus that number x we just found. And when we add those two numbers together, we end up getting 39.6, and we're supposed to round to the nearest meter, which ends up being 40 meters tall. So that tree, the estimate of the height of the Douglas fir tree is 40 meters tall. Okay, there is one problem left before you get to your homework. And that is, and now you try, and we'll read it together, just kind of underline the important information or highlight the important information. I'm sure you can already see, because of the way that it's marked, that we've got this same kind of altitude question. And it starts out to say, to estimate the height of Big Tex at the State Fair of Texas, Michael steps away from the statue until his line of sight at the top of the statue and his line of sight to the bottom of the statue form a 90-degree angle. So that's this 90-degree angle right here. His eyes are about 5 feet above the ground. That should say above. So this is the 5 feet height he's talking about. And he is standing 15 feet 3 inches away from big text, and that's this altitude. How tall is big text to the nearest foot? So the one thing I'm going to caution you before you turn off the video and get to work on this is some of our distances are given to us in feet only, but some of our distances are given to us in a mixture of units, feet and inches. So like always, we need to convert everything to either inches or convert it to feet so that we can do the whole problem in one unit of measurement. And then at the end, we're going to make sure that we're in feet and we can round big text's height to the nearest foot. So at this point, I'm going to actually show it both ways, in inches and in feet, but I recommend you turn off the video now, get some practice on this, and turn the video back on when you're ready to check your work. So we find to the nearest foot, big text is 52 feet tall. You can do the calculations either in inches or in feet, but in the end, when you are done with the problem, you need to make sure that the answer is given to the nearest foot. That is it for this section. You're ready to get started on your homework. And remember, if you have any questions, please bring them to class.